Okay guys, so COPD and asthma is still a very huge problem. And there's a lot of other diseases to the lungs, but only constricted gland disease such as asthma and COPD is the third global cause of death in the Western world. 7% of all the people in the world suffer from that. And one of the reasons is that we need better engineers to build better inhalers. And that's the reason we are here today, because you see the pharma companies start to give up on us. They start to use medicine, systemic medicine, to treat the lungs instead of inhaling something that can deposit directly in the lungs and reduce side effects. But to understand what's happening inside the lungs is very, very complicated. It's a very hard thing to do. So what I want to do, I want to use electrostatics in order to improve drug delivery to the lungs. But we need a better model, because we cannot use only this approximation, particle close to the tissue. And I use the electrostatic as a representative force, but it could be whatever crazy idea that you might have. It could be magnetic particle, it could be fiber particle, it could be magic particle. And you need a way to take complicated equation and make it a reality of a guidelines how I can treat the people. So what I'm going to present to you is this model. So you can look at the presentation. So that's what we're going to try to do. We're going to have this amount of aerosols, and they're going to enter some general generation of the lung, some cylinder. Some of the particle would deposit, and some of them would escape. And I want to have a method to estimate how much particles gonna escape and how much gonna deposit. If I can solve only this problem of a cylinder, I can treat all the lungs as an array of cylinders that I know all the parameters about them and can continue doing this loop until I have all the problems solved. So let's face the real problem. Okay, so we're going back to the drawing board. This is the vision, right? I'm gonna clean the board a little bit. Yeah, go ahead.
You're gonna solve this to one cylinder, right?
Yes, to one cylinder, and then I want to generalize it when we finish.
So generalizing would be connecting them in series and parallel, stuff like that?
Exactly. So the lung, I think that you're already familiar with that because you saw the records of Josue, but Josue taught us that the lung is connected in a very simple structure, the homogeneous splitting, and we know approximately what is the length and the diameter of generation, and you need that. This is what's called the Weibull model. There's a lot of models that build an array of cylinders that present the volume of the lung, the area of the lung, and that's the idea. We're gonna adopt that, okay? So let's go ahead. So we again gonna solve the question, what's happened to our particle? What's happened to our particle? Of course, we're gonna call Newton, hey, my buddy, let me understand what's going on. And to simplify things, we're again gonna assume a particle that, MA, right? We're gonna assume a particle that is not that small, but it's not that big. It's just in the middle for electrostatic to govern the deposition, which means the electrostatic force balanced by the drag force, and this is equal to 0. The drag force is very easy. We are talking about, this is a cylinder, right? So aerosols get into our cylinder, right? And the electrostatic force want to pull them in which direction? Radially, the closest to the tissue, which is radial. Right? What the question? What? Of course I can do that. Of course I can do that. Why I can do that? What do you mean? I don't divide by m. I do dimension analysis. I see what is the governed forces of the motion. No, it's okay. What does this present? Which phenomena? MA. Present inertia. This is inertia. And this is diffusion, of course, gravity. So if you do non-dimensional analysis, you can see in which cases, of course you cannot neglect everything. There's always going to be air around me. I'm always going to be next to Earth, unless we are in a SpaceX and we build inhalers for Elon Musk. That could happen, okay? And also this term is, you can treat it like a force. And you can see when this force is negligible. And if you're going to use some conditions, this term is negligible and is not going to be relevant. You can do numerical simulation, take into account also the acceleration, and you're going to do that in your final project. You're going to have the Eulerian approach and the Lagrangian approach. The Lagrangian approach would ask you solve this equation. And you can do that by using Runge-Kutta, a numerical solution, and you can leave this MA inside. And you're then going to use this approximation, going to see that the two graphs fit almost exactly, even though that you neglect it. Similar thing, you can neglect other. You just need to understand what is the non-dimensional governed equation. And this is the difference between physics department and engineer department, right? Sorry for that. Okay, so we're going to fight about that later, okay? But you are wrong. Okay, let's continue. The electrostatic force going radially, right? So Fe, I don't know how it's behaved, but it's related to the distance away from the tissue. I'm going to say only R because of the symmetry of the problem, and it's going to be radial, but I don't know how it's behaved in this big case of a huge cylinder when I'm not close to the tissue. Very dramatic. And the drag is generated because of the electrostatic force. So the drag's also going to be only at the radial direction, and of course it's come with the minus sign. So that's the equation, and what's really upsetting is that we cannot use the force that we used before, the image charge force. The image charge force is, let's do the function of R, let's do the function of Y, then a function of R. So this is Y, you see? Y, and this is the radial coordinate, so Y plus R is actually the radius, right? So it's behaved like K, Q squared, 4Y squared, right? And I want to change it into radial coordinate. So this is R minus R, right, squared, right? This is the equation, and you see that this doesn't hold. What should be the force in the center of the cylinder? In the center of the cylinder, yeah, we have a symmetry. So even all around me, I don't have any preference where to go. So we see that in R equals 0, what we got? Something wrong. So this is not hold. So what we're going to do, we're going to take an approximation. And now you are right. So we're going to take an approximation because, you know, the world is not perfect. So the actually force is, let's write it first. So the approximation we're going to take is R divided by R to the square. You see this? This image, force approximation, and we're going to correct it. Correction. It's not true. It's important to realize that, but this is an engineered tool to solve it. If you really want to see how much this correction is wrong or right, you need to really solve the equation. And if you're going to look at the presentation, this is the real force that we have in a cylinder. You need to use Green's function in order to solve it. We talked about it, right? And in the final project, one of the options is to take this force, plot it, compare it to what we did, suggest your other approximation, and you can solve and tell me how wrong I was, and continue the same derivation we're doing this lecture with another force, okay? But I want to remind you reality. You see, this is the cross section of the lung, of an airway in the lung. Is this a circle?
No.
No. So we approximate things. Is the earth is round or flat? It's round, but we always treat it as a flat in our calculation. We know it's wrong. So that's what I want to say. I want to say that it's an approximation, but it helps us. It helps us because the force is always increasing, right? Always increasing as you don't need to take only the board. Yeah. So the force is always increasing as I get close to the tissue. And if I'm gonna make if I'm gonna make R approximate to R, I'm gonna get back this term, the image force. So this force answer, let's write it. Let's write Fe approximately. It's not the truth. It's not the truth. Approximately. Also another thing, the cylinder is not infinitely long. So there's a lot of problems, right? A lot of problems, but we need a mathematical tool to estimate. So kq squared 4r minus r, and this is the correction that we're going to use. And this is good for two reasons. F at ER equals 0 equal 0, right? So this is good. The second thing is if we take the limit of R going into R of FR, we're gonna get the image charge. Image. We're gonna get image force. Image force, right? So these two conditions, and it's always increasing. It's getting stronger and stronger as you get to the tissue. So for that reason, we're going to continue with this force. But of course, I told you, you can check this in a final project. So if you're going to go with that assumption, so we have the equation that the electrostatic force, K Q squared 4R minus R squared, here I miss a squared, multiply by R divided by R squared minus the drag force, right? You see? So I can solve this equation, right? I have derivative, it's a simple OD. I can do again separation of variable, right? So I can reorganize the equation and get dr to dt equal to b k q squared 4r minus r to r squared. And now, look, this is a general case. It's specific length scale, right? But I want to make it general. I want to make it to be applied to every cylinder that I know. So what I'm gonna do, what I can do to generalize it, I can again make, what? Not to y, I can make my cylinder my R started 0 and end in 1. So I actually use R star, which is R divided by R. And now it's a general case. I'm solving for all cylinder that I want. If I'm in the middle, my R is 0, and if I'm in the end of the cylinder, I equal to 1. I use this variable. So we're gonna get that R equal R star multiplied by R capital, right? I'm gonna plug it inside and we're gonna get dr star divided by dt multiplied by R bk q squared 4r minus r star squared, and here I'm gonna have r star r square, right? If you're gonna rearrange it, we're gonna see this is r star square, right? R star square. This is, let's make it that way. So it's gonna be dr star dt equal bk q squared 4r to the third multiply by r star divided by 1 minus r star. This is to the power of 2, right? We don't have length in our equation. We simplify it. We are working from 0 to 1. What is the time scale of the problem? This have a unit of 1 over time. This doesn't have a unit, right? We divided by r. So this is 1 over our time scale. And look, it's the same time scale that we had before. Recall from the previous problem? LC now become the radius of the problem. So this is equal 1 over tau e of our problem. So tau e equal to 4r to the third bk q, and we can also say that q is what q? It can change, exactly, it can change in time. It can be tau c, right? We can do this again. So here let's put in our time scale q0 some characteristic charge. Yes, a question?
Also before and also here q square.
Yes, q square. Well,
You're green. Green q.
Here square. Thank you. Thank you.
And also,
Yeah. Thank you. Okay, perfect. Good. So we have that. We of course have that, and we can define time that compare itself to this characteristic time, the electrostatic deposition time, right? So of course we're going to have also here, if you're going to plug it in, t star, tau, we're going to get lambda. Again, lambda is tau e divided by tau c, right? So you're going to get that. Okay, so we're going to write the equation to tell us what's going to happen inside the lungs. Again, approximately. So dr star dt star equal r star 1 minus r star. This is square, and our exponent minus 2t star lambda, right? This is how our particle behave radially, right? Perfect. What? Tau e disappeared because we have here tau e, but we also have inside t tau e, right? So it's cancelled. That's the reason we chose it, to make the mathematics be simplified. That's the idea. One of the idea of non-dimensionals is also that, because I don't want to talk about specific radius. I want to normalize by the radius and talk generally about the problem of a cylinder, right? So I don't have units. I don't know if my radius is trachea, which is 2 centimeters, or it's a bronchiole, which is 1 millimeter. I can solve both for them, or the same equation. And the second thing this is convenient is the math become easy. Because if you normalize it correctly, all the parameters are gone inside your scaling, right? Perfect. So we have that and we have that. And right now I want to challenge you, because we don't really care if particle deposit or not deposit. We care where it's going to deposit, right? So a specific cylinder is not that relevant, right? So we want to talk not about the radial direction, but the penetration, right? So if this is a cylinder, this is the radial coordinate, this is the z coordinate. So this is very nice, but what I'm really interested about, and it's going to be important, we're going to come back to it, but what's really missing for us is to say, yeah, but would you succeed to penetrate this cylinder, or you're going to get stuck inside this cylinder? So I'm actually interested in dr to dt. Interested in dz to dt. Right? What would, yeah?
Are you sure that it is for cylinder and not for sphere?
Again, here?
Are you sure that it is for cylinder and not for sphere?
Because they use a force that's relevant to a cylinder and not a sphere.
not the particle is cylinder.
Yeah.
The tube is
No, the tube, because it is the solution for...
מצלמה? Camera? Yeah?
it is solution for sphere, but in cylinder there is
This is square.
כן, אבל שם כאילו בצילינדר זה חלקי 4.
Yeah, but I have the 4 inside my characteristic time.
Yes, and okay.
Okay, so I have 4 here. You are correct. So I already plugged the 4 inside my characteristic time. This is the 4. We're going to talk about it later. So if it's a mathematics error. Okay, so I'm back to here. We are really interested. Okay, we know how R change, right? But we want to ask what's happened to dz. What's happened to the particle at the z direction? What the particle is doing? Huh? We said there's no gravity in the z direction. There's no diffusion, right? There's no inertia. So only, and we don't have electrostatic because of symmetry, right? Electrostatic only radial. So the only force that can take the particle is the drag force, right? The drag force. So the air around the particle take it. Because the particle have a very neglected inertia, he immediately follow the flow. His MA is negligible. You can do it with the MA, put MA versus drag force, and you can see that the relaxation time for the particle to follow the flow is in the order of the microsecond. Very, very fast, okay? So, in the z direction, we can immediately say that the particle at the z direction velocity is equal to the flow. And what flow we have inside the lungs? Huh? We have Poiseuille, that's true. So Poiseuille said that we have twice the average velocity of that we have inside the cross section of the airway, multiplied by R over R squared, right? So that's how fast particle would penetrate into the cylinder. And let's write it in a non-dimensional way. How are we going to do it? So if this is a cylinder, and the cylinder is at length L, let's do it like this. This is Z, right? This is L, this is 0. This is a very specific case. We can have the non-dimensional axis that have here 1. And here is a location Z equal to Z star equals Z over L. You see it? So we can present any cylinder from 0 to 1. And then our equation become dz star over dt star. dz behave like L, right? And dt, if we substitute it, it's tau e, right? We want to compare the characteristic time to get trapped inside the cylinder or getting out of the cylinder. And here you're going to notice that we have 2 UF 1 minus R star, right? Square. This is already normalized, right? So if I'm going to reorganize this, I'm going to get a very interesting thing. And I want you to notice it, how time scales play in fluid mechanics problem. And in general in physics, yeah? We want to see how fast stuff happens. So I'm going to reorganize. So the rate I'm going to penetrate inside the cylinder, of course, normalize, it's 2 tau e UF divided by L 1 minus R star square. What is this? Who is that one? What is this term? Huh? Yeah, it's another characteristic time. This is the convective time. What is the average time I'm going to spend inside the cylinder? Right? The length of the cylinder divided by the average velocity of the flow. Right? So this one is tau convec. Right? So this is, by the way, a very important thing I want you to notice. This is very important for the final project. So I have in the final project a project that deal with charge decay, and every one of you can improve its project by incorporate also charge decay, and you can approximate how much time has passed in each generation by this parameter. You can say in the first generation, right, I spend time, right, I spend time of L average 1 divided by U average 1, right? And then I can see how much charge approximately succeeded to decay in my problem when I enter into generation 2. In generation 2, we're going to have T2 equal the length of the airway, right, of airway 2 divided by the average of 2, right? And then you can see that the exponent minus T over tau C is actually, can be written as sigma tau gen, T gen, right, divided by tau C. And you can approximate what's happened to this exponent. Is this clear? Important for your project. Yes? So this is an engineer perspective. I don't know where the particle actually is, but I know approximately how much time it's spent in the air, suspended in the air, in this generation. So this is just tips for your final project. This can be incorporated in every project. Okay, so we found the Z to dt, and we found the R to dt, and what I want to do is get elimination of time. Now I know how particle behave radially, and now I want to know how particle penetrate. So I know what is the rate of particle getting expanded, right, radially, and know what is the rate particle getting pushed into the other side because of the air. So what I'm going to do, I'm going to compare these two, and then we're going to have the golden method to evaluate what's happening inside our lungs. So what I'm actually interested in is we want dr to dz, right? Radially versus penetration. This is game over. This is I succeed. I get out. This is the ratio we're looking for. I don't know this ratio, but I know this ratio equal to dr squared dt squared dz squared dt squared, right? And I know each one of them separately, right? How these two behave? So dz, we just found that, is this one, is 2 tau e divided by the convection time, 1 minus r squared 2. And this one is that one, is r star 1 minus r star square, and we have the exponent of charge decay that we might have, right? You see that I have the electrostatic charge deposition versus the convection, and gamma, I remind you, it's the electrostatic charge deposition versus the dissipation of the charge. Perfect. This is cancel, of course. And we can write it organizedly. So this is equal dr star for every cylinder that start from 0 to 1, that end from 0 to 1, behave like tau conv 2 tau e r star squared 1 minus r star to the third 1 plus r star multiply minus 2 lambda t star. Okay? Very important equation. Let's take a break for 10 minutes and then reveal what we got. Okay? Okay, so guys, recap what we have done so far. We assume a mediocre size particle, medium size, right? Not too big, so gravity and inertia are not relevant, but not too small, so diffusion does not count. We approximate the electrostatic force to behave in that manner, like the image charge, with this correction. we said that the particle can lose the charge via time, right? We approximate an RC model, right? So we have a charge decay, and we say that the characteristic time of the charge decay is the ratio of the air property, the electrical air property. Permittivity versus conductivity. Then we define the characteristic electrostatic time deposition, which behave like this. And from that, we derive what should be our non-dimensional time unit. Why we did that? To make the equation a little bit more elegant. We define lambda, which is the ratio between tau E and tau C. How much fast I'm going to deposit versus how fast I want to decay and lose all my charge, right? Good. Later on, we also encounter T-conv, which come from the word convection, how much particle is moving by the velocity, and we can approximate this time scale for each cylinder by the length of the cylinder versus the average velocity of the air inside the cylinder. And we also make a general case for all the cylinders in the world by normalize them by their geometry, by the radius and by L. Then we wanted to evaluate what is the rate in which I'm going to deposit versus I'm going to escape. And I remind you why we're doing that. Look above you. We want a model that tells us how many particles get in, how much deposit in the model, and how much escape to the other side of the cylinder. If you can do it for one cylinder, we can do it to all the cylinders that make up the lungs, and we can evaluate what would happen. Good. So we're back here. So at the moment, I'm going to take an approximation to simplify stuff. So again, I assume that charge decay is not relevant. Okay, so I'm going to say let's do it here. For tau E much faster than tau C, the lambda go to 0, go to 0, and the exponent go to 1. And for that, we don't have this term. And then we can use separation, variable separation. We can use R star square divided by 1 minus R star square. If I want to solve it, dr and half tau conv tau E dz. And now we want to see a very specific case. I'm going to do the integral. And I want to do a very specific case. I want you to look at the presentation. Here it is. No? Here it is. Okay? So I want you to see that there is a specific critical R. You see it? RC. At this RC, which must be smaller than 1 if it's normalized, if I'm going to trap at this region, no way I'm going to escape the deposition. You see what I mean? And if I'm smaller than this R, I'm far away enough from the tissue, and the Poiseuille flow of the air would drift me away outside. So actually, I'm going back to the board. So actually the probability to deposit is actually the flow rate that's gonna deposit versus the total flow rate, right? Because the particles are suspended in the air, right? So this ratio is what's going to tell me what are the odds they're going to deposit or not deposit. The question. Where? Here?
No.
What?
Small.
This one?
Yeah.
That's true. Okay. So let's correct that. So 1 minus R star to the third, 1 plus R star square. Again, I'm going to repeat it. Then, focus. I'm going to repeat it, it's very important. We had this equation. Oshri, we had this equation. This equation tells us how much particles want to deposit radially and how much you want to penetrate to the other side of the cylinder. And right now, we want to evaluate this equation. We're going to do separation of variables like this, but I'm going to choose a very specific integral boundaries. I want you to look at that. At specific RC, if I'm going to be at RC star, I for 100% gonna deposit. In which location? Z equal to 0. I'm starting in this place. If I'm starting at RC, at the location Z0, I'm starting at that location. Let's do star. And I'm gonna end up at R equal to 1. That's the critical RC that's gonna deposit inside the cylinder, right? And Z gonna be equal to, I just arrived to the end. Why this is very important to me, these boundaries? I'm going here. The probability to deposit inside the cylinder, I'm going back to that, is the total air flow rate, the flux of particle that's gonna deposit divided by all the particles, all the flux. So all the flux is pi, right? R square, U average, right? But what are the particles that for 100% gonna deposit? It's the double integral, right, on the velocity as function of R. dr r d theta are gonna run from 0 to 2 pi, all the cylinder, symmetrical problem, but only the one that's gonna deposit are the one that close at RC, right? And getting to 1. All of these particles, for 100%, gonna deposit inside the cylinder. So if I can evaluate, look, I know everything here. I know Poisson, right? The only variable that I have is what is this RC, right? So this equation, I'm going back to here. I know this connection. I can do separation of variable. I neglected charge dissipation, right? I get rid of the exponent to make our life easy. And now I can have an equation that the only thing that is missing is what is RC, this variable. If I know this variable, I know the probability of particle to deposit. So if I'm going to solve this, I'm going to get 2 ln RC square, not square, star, sorry, non-dimensional. I remind you, RC star is just the real RC divided by R. Because I don't really care about RC in a specific cylinder, but I'm looking for all the cases, all the cylinder, there's a characteristic R, a specific, it's not a characteristic, sorry, it's from the word critical. There's a critical R that I'm too close to the tissue and I'm going to deposit for 100%. And a third RC, R critical to the third, minus 1, minus R critical squared, plus 1 over RC squared, and not square star, equal to that thing. Which, you know, it's the same because I integrate from 0 to 1. So I don't have any Z. Right, so it's the same. Half tau conv, tau, this is tau E. Right? Here I found it. I can't solve this. Why? It's inexplicit. I cannot solve it analytically, but I can just put, and this is the reason this final project is on MATLAB, because I can say solve. And it's gonna find RC, solve for RC. So you can do it with MATLAB or other program that you would like. And then I'm gonna find RC. I can plot it here, and then I can calculate what's gonna be the probability of particle to deposit in that cylinder. Is that clear? Yes, it's very important. This, I think in every project, you need to plot what is the probability to deposit in the lung. What we're gonna do next, okay, I'm just gonna tell you conceptually what we are doing. You have here the time? Yes, okay. So conceptually, now I know the probability to deposit in a specific generation. I can put here gen, I can put here gen, right? Gen, this is U of some generation, this is U average of some generation, this is radius of some generation, right? And I can plot all the probability of every generation, right? This is the probability here, 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 here. Why the probability increase to deposit?
Because the cheek gets narrower, so the front.
One good point. As we go deep inside the lung,
Less particles and
the velocity reduced. I have more time. So the Poisson that pushed me to the other side got smaller. Another thing, tau E, what is tau E equal to? R to the third.
So if it's bigger than that, it will probably deposit.
Yeah, so the time to deposit become much shorter because we close to the tissue. It's proportional to the R to the third, right? So probability increase, but don't forget, we also have particles. So if the particle here deposited, they are not available anymore to go to the next one. And this deposit, they are not available to get to the next one. And this not here. So I not promise you, even though here the probability is very high, nobody is promising you that you would left with particle to go there, right? We have what's called screening effect, right? Like everyone is a screen that block you to get to the other side, right? Another thing that it's very important to take into mind, okay, so that's, this, if I have this aerosol cloud with particles, and it's got into this generation, right? And some of them deposit, right? And some of them survived, right? What's going to happen now? They need to split, right? So each one going to go to these two. So you need to do two things. One, you need to split them, right? And you need to multiply. You need right now to solve this problem twice. You have the result, right, from here. Half of the particle got into this place, right? Solve it and then multiply to have what?
That's when you're going to use the Weibull model?
Yeah, what? Again?
That's what you're going to use the Weibull model?
Exactly. So you're going to say this was L by Weibull model. This was D by Weibull model. Let's say trachea, LFS, L0 and D0. This would be L1 and D1, right? And that's going to continue, right? So you need to be careful to account to that screening effect and also to the multiplication of generations. Let's see some example that I want to see in the project, in your final project. So look at that. Look. Wait. Where is it? Where is it? Ah, I don't have it. I do have it. Wait a second. Don't, close your eyes. Close your eyes. Don't look. Don't look. Don't look. Where is it? Maybe it's on hide. Okay, never mind. Okay. Okay, never mind. Okay, so here you see the probability. Here you don't see the probability, sorry. Here you see the position fraction, which means I release 100 particles at the trachea, right? And you're gonna see how they're gonna distributed along my lung model. And if you're gonna look here, I put a very neglected amount of charge, 10 electron. That could happen by accident. If you have a nebulizer and it's working, this is probably the charge. And if you see my model, you see that only 4% deposit in the model. You see it? Only 4%. My model was one directional, but actually you have inhalation and you have exhalation. So how many particles would deposit in my model? 8%, right? Not 4, sorry, but you have 4 in, 4 out, right?
Twice as much.
Twice as much. And what's really cool is this is exactly the value that you get for human experiments. If you use half of micron uncharged, this is the result you have. Approximately 10% of the particle would deposit inside the lungs.
Except of tidal volume, we need also to calculate the position in the alveolus.
That's a very good point. So in our model, we neglected the alveoli structure, right? We just use cylinders. But the same solution that you saw here, we have the same thing, even simpler one, for the alveoli. Because in the alveoli, you have a sphere and the electrical force is more easy to understand. Okay, so let's increase the charge. Are you ready? Charge 2. Whoa! I changed from 10 electrons to 100 electrons. And what I see, that 50% of the particle deposit. As you can see, the chances were better at the end. Why? Velocity smaller, radius is smaller, right? Time is very short to deposit. Let's increase the deposition. Whoa! If I use thousands electrons, I even see a peak. This peak takes place in which generation? 16, 18, 19, right? This is the respiratory zone. This is the region if I want to treat persons systemically. You have a headache? Take this inhaler, it will help you. You need insulin, you have a diabetes? We can engineer the drug. Let's increase the charge. 5,000 electrons, all the particle deposited, no one escape. Everybody find himself deposit in some region. And what I want to show you that before, we were targeted in generation relevant to the alveoli. But if we increase the charge, we're actually taking the particle a little bit back. You see it? You see the presentation? This is the bronchiole. This is for patient needed for asthma and COPD. So we can use the electrostatic charge in order to govern where particle would deposit inside the lungs. And we prove it in an experiment. So this is a paper that I published with amazing people that are here in the audience. And we build this lung model, lung on a chip. And we split this model into 4 regions, bronchi, proximal bronchiole, distal, and acinal. And the distal bronchiole are actually the region that today we are fighting very hard to target and to treat people. Because you see, it's very hard to target this distal region. And instead of that, you have a lot of side effects. You get into the acinar region, you get to the blood, you have extended heartbeat, you have headaches, you have nausea. So when you add the electrostatic, you have this screening effect going back, and then this is the deposition pattern. So you can use electrostatic to target the distal region. And what we saw in this experiment, we saw that we have approximately 5 more time particles in the right place and not in the wrong place. And that's also happened way faster because the electrostatic force have its own time scale to deposit. So that's happened in a quarter of the time, sorry. So quarter of the time, 5 times more medicine. This is 20 times better than off-the-shelf nebulizers. So the only thing that we didn't talked about here is we also expected to have the position in the mouth and throat, right? And this model doesn't have mouth and throat, right? So there's a model to approximate it, and theoretically, we saw that we have increased the position in the mouth and throat, but only by 3%. So this is a very good price to pay. And but we're still working on other ideas in the lab to improve it. So we took inspiration from asbestos that penetrate very easily because of its fiber shape. And right now we're producing particles that have fiber shape and charge, as we discussed today. And the idea is to make, the ultimate inhaler. So we call it FibreF because fiber and also the electrostatic FibreF. So what is the idea of your final project? So in a final project, you're going to play a little bit. Let's go to this. Here it is. So in your final project, the idea is to play with everything that we have learned. We learned about the electrostatic force, and I think it's a great example for an exotic force that you want to apply. and I want you to play a little bit with the force itself. I talked to the physics persons here, that they can play with a more realistic force. You can play with the charge decay to see what the effect of the decay. You can play with the breathing patterns. Somebody that breathes fast, somebody that breathes slow. You can play with the combined effect. Here we did only electrostatic, right? But if instead of using half of micron, I would like to use 2 micron particle, gravity is not neglected anymore. So what you need to do, you need to plot a probability, right? P versus gen, right? Plots. You also, and this is going to be kind of a Eulerian approach, right? You're doing that. But you also can do Runge-Kutta, which actually going to solve the particle dynamics. So you're going to have a path of a particle do whatever you want, right? To the 4th order approximation. So you can do that, you can compare. You can also do non-dimensional, right? Non-dimensional analysis. Dimensional. So that's actually going to plot x versus y, right? That's going to be probability, and non-dimensional going to tell you something about who is dominant, and you can compare this and play with the parameter. You have a question? What? At what? What we printed? Okay, so we use a glass and we coated the glass with the ITO. And the ITO mimic the conductivity of the tissue. Definitely, I want to mimic the image force effect.
The tissue is moist.
No, that's a very good point. I put a dry air. That's a good point, and I mentioned that in the paper. And I approximate, the RC model came from one of the, how you say it? When you submit a paper, they review the paper. So the review said, what about the humidity? And I said, okay, let's find out. And then I came up with this RC model and and I saw what would be the cases. But you're right. A better experiment would be with humidity. What?
הפורמט כאילו הזכוכית, אם אני שם זכוכית, אז היא מקבלת מטען דווקא מנוחות. בגלל זה שאלתי.
Yeah, everything is, the ITO is grounded, yeah, everything is grounded.
זה לא משנה, זה לא מוערך, אבל יש לך תוצאות תאונות.
You know what the definition of model is? Not the reality, it's a model. So you're always going to be this gap. Yeah. Okay, so what's really comfort me is that there was, in the past, and you see that in the final project I put a lot of old papers, because people of electrostatic are old people, yeah, it's not a new thing, but the community doesn't take advantage, as I see it, the potential that we have from electrostatic, because for the people that deal with medicine, this is too complicated, and I can understand, right? It's not an easy stuff, even for an engineer. So this kind of area left behind. And I said, why we should not bring it back, right? And there's experiment on human that showed that electrostatic did matter. So it means that humidity play some role, but doesn't decay the charge immediately. Yeah. Okay. So that's for today. And what I want you to do is, I want you right now to read the project that you have. You need to tell me which type of project would you like to do. Electrostatic with gravity, right? Charge decay. Improving the electrostatic force. You have a lot of areas. You also have a project of building a nebulizer. So you can go and check that one. And also electrostatic and diffusion. I can take particle to make it bigger and then account for gravity and impaction, but I can make them smaller and talk about diffusion. So, and the idea of this lecture was to give you these tools, how to have the probability. Runge-Kutta for, guys, you can open MATLAB and YouTube and ask chat, make me a Runge-Kutta 4. So I'm not that worried about that. Non-dimensional, you work all the semester about that. You know how to define them, you know how to work with them. And I want you to make a very good case and discussion and investigate and tell me things that I don't know, okay? So that's the idea of the project. Good? Perfect. So thank you very much for the semester. I don't know if you know, but this was a surprise to me that I'm going to teach this class, because Josue was not available to do it, and I told him that I'm going to do it in a mixed effect. I'm going to contribute where I can, and where he can, he's going to contribute from his records, and I hope this class was beneficial to you. This is our last lecture, but I'm going to be available anytime. Just talk to me, right? Or send me an email. Feel free. And I'm very excited to see your work. So you need to submit your proposal to the end of the semester so we can approve it. And then in the time we're going to dedicate to it, you need to submit it.
Until the end of the semester?
Huh? What? Your proposal? I think, yeah. But huh?
איזה נושא עושים?
Yeah, only which proposal you are doing, and you need to find supported papers that are not in the Moodle. You need to find supported papers that you found. Yeah.
איזה נושא את עושה ואיזה מאמרים את משתמשת וזה כאילו הקצאה.
Yeah, that's enough.
לא, זה לא עד סוף סמסטר, זה עד שבועיים אחרי הסמסטר.
לא, אבל כאילו, כעיקרון, יש עם זה בעיה, כי אי אפשר לעשות את זה עד שבועיים אחרי הסמסטר.
אבל יש לי גם עוד שבועיים.
Okay, so you talk with Dana. Whatever Dana is happy with, I am happy. Huh? No, I really don't mind. It's your project, guys. I'm fine with that.
אם כבר אנחנו בעניינים טכניים, ההגשה היא לראשון לספטמבר. אפשר להריץ את זה?
We just talked about it. I don't mind. Talk to Dana, and you decided whatever fits for everybody.
תודה.
Thank you. Yeah. Question.